Hi everybody and welcome back. So, today's lecture is going to be about a fascinating topic, which are curves over finite fields and their maximal number of points that they can have, the maximal number of rational points that they can have. So it's a very important topic. Plenty of people are working on this topic, and because also there are applications to error correcting codes, and I'm not going to say much more about this, but you have like some ideas in the notes of the course that I always tell you about. So when you want to know more about these lectures, look also at the note of the course. They are really complementary somehow. So, but let me tell you, it's, as I say, it's a big topic, but I'm just going to tell you the basic, how it works. So maximal numbers of rational points on curves over finite fields. So we fix a curve C over a finite field FQ, so C, smooth, absolutely irreducible, projective curves of genus G. All right? And we saw, in the previous lectures that at least you can understand the number of points on the curve thanks to the zeta function, and because of the Riemann hypothesis, what you have is that this number of points is always going to be less or equal to 1 plus q plus g times 2 square root of q, right? That's the bound that we found and which is called the Haas-Weil bound. And well, let me say first, maybe as a consequence also, maybe I should write it more in this way. This is really Haas-Weil bound. As a first consequence, if you look at it, it means also that as soon as Q is going to be big enough, if you do the inequality in the other direction, you see that the number of points on the curve is always positive. So there is always one rational point, which is always a nice thing to have, as we will see in the next lecture when we speak about Jacobians. But as I said, the topic is more about like how close the number of points of C over FQ can be of the upper bound. We have now an upper bound, and we have to say, is it reached? If it's not reached, what is the maximum? And for long, it was thought that, it was like mostly optimal. But as we will see, it's not that easy. So in order to understand this maximal, that's what people do. They denote NQG. So the maximal for all curve C over FQ with the genus of C equals G of the number of points, rational point on the curve over FQ. And okay, so what can we say? First, there is a slight improvement that we can do. You see that this number 2 square root of q, when q is not a square, this is not an integer. So, of course, we can take the integer part of this, but what Serre proved is that you can do slightly better. So, and this is the following proposition, which is also theorem 6.2.1 in the notes. And it's called Haas-Weil-Serre bound. And it says the following, that the number of points of C over FQ is less or equal to 1 plus Q plus G times the integer part of 2 square root of Q. The proof is not complicated, and I'm going to give it because somehow you will see that in the next lecture, we are going to use part of this proof to get also something very interesting on the zeta function, on curve in some special cases. So let me give you the proof. So remember that we wrote that the number of points of C over FQ is 1 plus Q minus the sum from A equal 1 to G of alpha I plus alpha I bar, where these are the roots of the numerator of the zeta function. Now, let's define xi as integral part of 2 square root of q plus 1 plus alpha I bar. Okay? Because of the result on the norm of xi, one has that of alpha I, one has that the xi are positives, and they are actually, because they are, well, I first maybe should say this, this is a real number, and so xi are totally positive real number, meaning that all the conjugates of xi are also positive. So xi are totally positive algebraic number, but even better than this, one can easily see using the Vel polynomial or the numerator of the theta function that they are actually totally positive algebraic integers. And from this, one can deduce that the product of all this number must be at least 1. Now we use a famous inequality, the arithmetic geometric mean inequality, to see that 1 over g times the sum of the xi is greater or equal to the product of the xi from 1 to g power 1 over g, and this is of course still greater or equal to 1. And now if you do the math, so the sum of the xi is going to be bigger or equal to g. If you inject what are the xi, what you get is that the sum of the xi is greater or equal to g, and you get the Haas-Vel bound. Okay, cool. Now what? Now, even like seeing the definition, of NQG, there are two parameters. There is the Q parameter and there is the G parameter. And so usually when people try to get this number NQG, they draw tables, as we have seen in the first lecture. So you have your table. Here you would have Q, and here you would have G. In here they put primes and also the power of primes maybe, and so on. And here they put the genus, so let's say genus 0, 1, etc. And you try to get for each box, let's say here you would have genus 1 over F5, what is the maximal number of points? So of course you will have an upper bound, which is at worst Haas-Vel bound, and you try to get a curve of genus 1 over F5, which reaches this upper bound. If you can, then the box is done. There is nothing more to do about it. But sometimes, as you will see, if you look at the website, so everything is now online on manypoints.org. If you go on the website, you will see that there are plenty of boxes for which we don't know the answer. And also, the thing is that there are two directions. You can either say, I will let Q fixed and let G goes to infinity and study if I can say something for a given Q and for like infinitely many genus, or you can take the converse problem. So you can fix the genus, for instance genus 1, and let Q vary. Okay? And these two directions have been considered by Jean-Pierre Serre in his famous course in Harvard in 1985, where he divides really, the lecture in two, and actually he was dividing even the schedule in two, like having one day where he would do like horizontal studies and one day where he would do the vertical one. So we will say a bit about these two directions. And let me start with the direction where I fix the genus and then I let Q go to infinity. So this is the case of G fixed. First, let me say that when Q is going to become large, okay, in comparison with the genus, Hasvel-Serre bound is the best upper bound we know. There is no improvement in general of this Hasvel-Serre bound. It doesn't mean that you reach always Hasvel-Serre bound, as we will see, but we don't know how to do better. So that means that in this table, when Q is large, usually what you have is exactly this number, except in very, very particular cases. Now, I mean, the story ends up very quickly because we know NQG for all Q only if G equals 0, where it is Q plus 1, G equal 1, and G equal to 2. So yeah, I mean, the story ends up very quickly, and even, I mean, over for G equal 1, I mean, this Hasvel-Serre bound is not always reached. Let me give you some example. So over F7 to the 5th, NQ1 is not 1 plus Q plus integral part of 2 square root of Q, but it is this minus 1. And if you want another example, in Genus 2 over F31, and Q2 is 1 plus Q plus 2 times 2 square root of Q, but this times minus 2. And so the answer for Genus 0, I mean, was known since, I would say, forever. For Genus 1, this is the result of during in 41. And for Genus 2, that was what Serre did in his lecture. So he gave the proof in his lecture in 85. What else can I say? I mean, you see, I mean, the story ends up quite quickly. I can also give you maybe what are the first challenges that you can find on this table. What would be the first boxes that are not complete? So the first challenges that you can find would be, so what is N29 of Genus 4? Here there is still a gap. And N11 of 5. Here also there is still a gap. Remember that at the very, very beginning, we had like one goal. At the very beginning of this course, and also the course that was, the goals that motivated the course of Anna and the goals that motivated the course of Stefano. The goal was to study the case of, so our ultimate goal was Genus 5 curve over F47 with 113 points. I mean, we wanted to know if such a curve exists or not. And I just want to point out here that, I mean, what is known is that if you look at the tables, there is a curve with 108 points, okay? And that 130 points, I mean 130 is Hasvel-Serre bound, okay? So it's exactly the maximum. Our goal is to try to see if we can reach the maximal number of points, or if one has to go down, and we would have to go down up to like maybe 5 less than the maximum. So that's our goal, and you will see in the next lecture that I will try to come even closer to the goal, like with the tools, trying to put a bit together what has been done by Stefano, Anna, and I to try to study a bit more this problem. Of course, I mean, I'm not going to go to the end, as I said. I mean, it's still an open problem. But I'm going to tell you what could be a strategy. And let me also give maybe what is in this area, like maybe the ultimate goal. I mean, I call it Serre's challenge. It could be Serre's question. I know there are so many of them, but I mean, what he says, I mean, what he finds, what would be the most interesting problem to study in this area would be the following. It would be to prove that for all G, and actually you could be much less ambitious already, and it would be a great success, would be to do G equals 3, would be to prove that there exists a constant delta, so depending only on G, such that for all Q, NQG is going to be greater or equal to 1 plus Q plus G times integral part of 2 square root of Q minus delta. So what it means is that up to something bounded for each genus, Haas-Vell-Serre bound is quite optimal. It's not too bad. And that would be really nice. But we are really, really far from getting such a result. I mean, even like as I said, for genus 3, this is not known. For genus 1 and 2, we have formulas, and it's easy to see that indeed, I mean, it's bounded by, in genus 1, I think it's 1, and in genus 2, maybe it's 3. Okay, let me also give you maybe one exercise. I mean, to see that even if we can't populate these tables as much as we want, we can always at least find some boxes that we can fill. So, exercise. So consider what is called the Hermitian curve. And it's not really like, well, maybe the most known equation, but this is one of them. So let me write it projectively for you, plus y, so I'm going to call it h, and over fq square. As the first question, show that is smooth and absolutely irreducible if you want. But if it would not be as a plane curve, it would be easy to see. Show that the genus of H is so Q times Q minus 1 over 2. And now for numbers of points, so using that the functions that go from fq squared to fq, which is called the trace, which has x mapped to x plus xq, is surjective. Prove that the number of points of h over fq squared is q cubed plus 1, I think. And then 4, conclude that h over fq squared, which is Haas-Vell-Serre bound. Cool. I mean, that would prove that, I mean, in some cases, you see very I mean, the genuses are not all of them, so you have not everything you would like, but you have some boxes that you can fill, at least when you are over a field which is of the form fq squared. Okay. So now I'm going to go in the other direction, meaning I will let Q fixed and G grows. Okay, so as I said, somehow in this case also have like a lot of motivation. So it is motivated by coding theory, and I let you read the section 6.3 in the notes if you want to know what are the relations between curves or finite fields and coding theory. It is quite a big success of algebraic geometry in the application, still nowadays. And so, because we are going to let G goes to infinity and try to see a bit asymptotically how it behaves, one introduce what is called the Hirara constant, so A of Q, which is the lim sup, when G goes to infinity, of the number of points of n qg over G. Okay. And the first thing that we can notice, but as veil Serre bound, what you see is that A of Q is going to be bounded by integral part of 2 square root of Q. But now, that's the story. As I said, in the direction when you go horizontally with G fixed and Q is big in comparison to G, then Has-Veil-Serre bound is right now the best bound we know in general. But in this direction, when G is going to be big in comparison to Q, this is not true anymore. And as a first example, it's what Hirara did, and it is based on the following idea. You're not only going to use the fact that you have point over FQ, but that you also can look at the points over the extensions, and in particular FQ square. And because you have here a curve over FQ, the point over FQ are of course like a subset of the point over FQ square, so you need to have such an inequality. And then you reinterpret this inequality in terms of the usual formula. So this is going to be Q squared plus 1 minus the sum from E equal 1 to G alpha I square plus alpha I bar square. That you transform ISQ square plus 1 plus 2GQ minus the sum of alpha I plus alpha I bar square. And now you use Cauchy-Schwarz inequality to get that you have Q squared plus 1 plus 2GQ minus 1 over G, the cardinality of the curve C over FQ, minus Q minus 1 square. Okay. So this number appears now on both sides. So we are going to get some inequality. It's quite ugly, but after some computation, this is what you get. So the inequality you get is that the number of points of C over FQ is less or equal to Q plus 1 plus square root of 8G plus 1 times 8Q, plus 1G square plus 4Q square minus Q G minus G everything over 2. It's not even clear that it is better than Has-Veil-Serre bound, but let's see, because if you do at the limit, what it gives you, if you divide now by G and you let G goes to infinity, what you get is square root of 8Q minus 1 over 2, which is the square root of 2Q minus 1/2. And yeah, I mean, indeed, this is better than this bound. Well, I mean, when one has such a nice formula, then the idea would be, of course, also to consider the number of points of FQ cube, FQ fourth, and so on and so on. This is the beginning of the trick, but of course you need like much more like subtlety to try to put all the information together in a nice way. But this is what is done, and you can have a look at the theorem, which is theorem 6.2.4 in the notes, and it is called the Drimfeld-Vladuc bound. And you can go up to square root of q minus 1 for the upper bound on AQ. So you see that in this direction, Haswell-Serre bound is not the optimal bound. You have something which is much weaker. Now again, one has to consider the question, is this value reached, or is this bound still too large? And for this, again, one has like several cases to consider, and the case which is very well understood is the case where Q is a square. So, theorem. Yara, Sassman, Vladuc thing says that when Q is a square, A of Q is square root of Q minus 1. And what I would like to show to you, right now and for this end of this lecture, is that in the case where Q is P square, so A of P square is P minus 1. And it will be, of course, a bit sketchy. I can't give all details, but I will try to be, at least to give you like the big intuition which is behind. All right, so the idea was to give you the proof of the fact that AP square is P minus 1, which means that we will need to construct, if you want, like for infinitely many genus, like genus growing, curves which have many points. How are we going to do that? As I said, it seems already difficult to construct like genus 3 curves that have many points. And in general, if you even like to try to say, okay, can I even show you a curve of genus 100 or something like this? Is it possible? Can I do this? In general, it is difficult. There is a theory by Petri in 1922 where he says, I can describe all kind of curves, and then Mumford a bit later in his book, the Red Book of Schemes, and the lectures that are at the end say, that's wonderful theory, one should be able to apply it to something. And then in 2002, Schreier comes and he says, no, there is no easy way to deal with that if you want to deal with that explicitly. Gröbner basis is not going to help you to solve the different equations you have to solve between the coefficients in order to describe a curve of genus 100, for instance. So it seems that we are stuck. But the idea is that, luckily, if you want, or I don't know if it's luck, but at least it is quite a very nice coincidence, we know some families of curves that we can describe in other ways, and for which we will be able, one, to give what is the genus, and two, to describe a lower bound on the number of rational points. And these curves, they are the modular curves. And it's a very fascinating history that modular curves that are so powerful in Diophantine geometry come again like to play a role over finite fields. So I think it is very nice to see it like that. So let me try to give you some elements of the proof. So for n greater or equal to 3, there is something which is called a moduli problem. Okay, which is to describe here or classify elliptic curves with a cyclic subgroup of order n. So meaning that Q elliptic curves, let's say over a field, with a cyclic group, here C1 and C2, they are going to be considered as equivalent if and only if there exists an isomorphism from E1 to E2 such that phi of C1 is C2. Okay, very nice. What about this? I mean, what we can say is that this moduli problem, so Mn, is representable, meaning that there is a curve, projective, well, let's say start with affine first, an affine curve over spec z over 1 over n, meaning that if you want, you could describe it by equations with coefficients are integers up to maybe denominators which are power of n. N such that for any field K, so this affine curve, well, I mean the points on it are the couple C, EC defined over K up to equivalence. Okay, but this is an affine curve and we don't want to play with affine curve, so there is always a way to compactify it. So here one has to add a couple of points and so one can compactify it as a smooth projective scheme over still over spec. And it has the following property. If I look at it over the complex, it is the classical modular curve that is denoted x0n, which is the compactification of the quotient h over gamma 0n. So what is h? As usual, h, this is the upper half plane, so there's the z in C with imaginary part which is positive. And gamma 0n, this is simply the subgroup of matrix inside SL2Z, so with coefficient A, B, C, D, such that B is congruent to 0 mod n. And if you take the torus interpretation of an elliptic curve, as it was given, for instance, in one of the first lectures of Anna, then you will see that indeed, doing action of SL2Z I mean, all the action of SL to Z would just classify the elliptic curve up to isomorphisms, and imposing this condition then gives you what you need to also classify the cyclic part. Okay, but thanks to this interpretation, I mean, because we have this quotient, and then, I mean, computing genus is just to look at the points which are like stable, and also, of course, at the cusps, which are the point at infinity. Looking at all this, you see that the genus of x0 to the n, x0n, sorry, is roughly n plus 1 over 2, and I will restrict to n congruent to 11 mod 12, where this formula is exact. So one knows the genus of this curve. Cool. But I mean, here it's a curve over C. But the good thing is that, as we said, I mean, the moduli problem, I mean, has somehow a universal solution over spec Z over 1 over n. So it means that for any prime P not dividing n, x0n has good reduction. So you can simply take the equation over spec Z over 1n, reduce them modulo P, and you still get the curve which is a smooth projective curve, absolutely reducible, and of the same genus. And I'm still going to denote this curve x0n. So, but now I'm looking at it over Fp. Okay, cool. Now we need to speak about the points. And we are going to consider, remember, I mean, what we want is AP square, so we are going to look at the point over Fp square. So Fp square, rational points of x0n. What are they? So I need a lemma to understand the following. So I take E, a supersingular elliptic curve over Fp bar. Then one can prove that G of E is actually inside Fp square. So E can be defined over Fp square. And the Frobenius endomorphism, so over Fp square, acts as epsilon times P, where epsilon is an automorphism of E. Okay, let me prove that for you. So E supersingular, I mean, there are plenty of characterization to be supersingular, but the one I will take is that EP over Fp bar is empty. Well, is 0. So there is no P torsion points. So now if I take the Frobenius, which go from E to E sigma, where sigma inside gal of Fp bar over Fp is just sigma of x is xp. Okay, if I take this Frobenius, and it has a dual, I mean it is an isogeny, and it has a dual, which is sometimes called the Verschiebung. So here, the Frobenius, the dual of the Frobenius, it goes from E sigma to E, and as every dual, it has a property that Frob, dual, Frob, this is just the multiplication by the degree. All right, and what do we see? I mean, this has zero. I mean, it has a kernel which is just reduced to zero, so it is purely inseparable. We knew that this is, of course, purely inseparable as usual, but what we deduce is that the Frobenius dual is purely inseparable. Okay, so if I try to now have this thing, so I go from E sigma to E with the Frobenius dual, I can go from E sigma to E sigma square using again the Frobenius, but as the Frobenius dual is purely inseparable, it has to factor through the Frobenius. That's one of the properties of being purely inseparable. But the degree of this is the same as the degree of Frobenius, so it means that if it factors through this map, this is an isomorphism. But now if it is an isomorphism, the G invariant of E sigma square must be the J invariant of E. And this is the J invariant of E sigma square. And from this, you simply have that G of E is inside Fp square. And what is nice with elliptic curves is that when their invariant is defined over a field, you can see, for instance, using at the chapter 3 of the book of Silverman on elliptic curves, that you can always write a model using this number, which is also defined over the same field. So very nice. I mean, we have a model of the elliptic curve which is going to be defined over Fp square. And using the same arguments we have here, but applying them to the Frobenius endomorphism, which is just Frobenius composed with itself, then, I mean, you also see that you have the second property, meaning that, where did I write it? Yeah, the Frobenius endomorphism must act like exactly like P times any, not isomorphisms this time, but automorphism, because now we have E sigma square, which is just E. Okay. Nice. Now, let's consider E supersingular with J invariant different from 0 or 1728. So excluding these two values means I don't want any other automorphism on the curve than plus or minus 1. Right? And can I find such a curve? Does it exist? Well, in general, no, but I mean, it exists as soon as P is going to be greater or equal to 13. And they are roughly P minus 1 over 12 of them. Okay? So here again, I mean, I do some restriction because I'm not going to consider P small, but of course, I mean, all these gaps can be easily filled out. Now, another lemma. So I take N prime to P, and I say that the cyclic group, or the cyclic subgroup of order N of my elliptic curve E over Fp square, so E supersingular, are all defined over Fp square. So this is, of course, a very strong property. In general, if you take an elliptic curve and I say I'm going to consider a point of L torsion, whatever is L, there is no reason for this point to be defined over the field. I mean, if you look, I mean, there are solutions of a huge polynomial of degree L square minus 1. There is no reason for this point to be defined over the field. Of course, here it's a bit weaker because I don't ask a point to be defined, but just a cyclic subgroup. But even in this case, I mean, it's still like quite a strong result. And it's because we are really going to use that we are working with a supersingular curve. Why? Because let's take P inside my cyclic group. So the cyclic group inside C, cyclic subgroup. Okay? And I want to see that P sigma, where what is sigma, where now is an element of gal of fp square bar over fp square, which is just sigma of x now is x to the p square. I want to see that P sigma belongs to C. Okay? But why is that the case? I mean, simply because now, as I take the action of sigma, which is the action of fp square, this arithmetic action is given on the elliptic curve by the Frobenius endomorphism. So P sigma is just the Frobenius endomorphism applied to P, and we have seen in the previous proposition that this must be an automorphism, but in that case I have excluded all the other possibilities and plus or minus 1 times the characteristic P times a point P. And obviously, I mean, this is still inside the subgroup C I have chosen. So the subgroup is stable. Okay, so we are progressing. Now, how many subgroups do we have? So let me take so n prime to simplify a bit. So we know that because P doesn't divide n, En is actually z over nz square. So one is to choose a cyclic subgroup of order n inside z over nz square. It is as to choose a line in A2 over z over nz. Or, so it is, so a subgroup of order n corresponds to a line in the affine plane over z over nz, or to a point in P1 of z over nz. So how many do we have? So they are n plus 1 subgroups possible. Now we put everything together. So what do we know? We know that the order, the number of points over fp square of my elliptic curves, at least you will have all the points which are supersingular curves with any subgroup, because we have just proven that the subgroups are defined over fp square, that the super elliptic curves are defined over fp square, so all of these ones correspond to point over fp square. So these numbers has to be at least, so we said there is n plus 1 times the number of supersingular elliptic curve, and I said that they are roughly p minus 1 over 12. Now you divide by the genus, and you see, because that's what we proved, it's not on the blackboard anymore, I think, yeah, that the genus was n plus 1 over 12. So that you get a nice cancellation, and you get at least p minus 1, but we know that p minus 1 is the maximum. So A of p square is p minus 1 as we want it. Okay, thanks a lot.